it is about that time. So we have this room booked for about an hour and a half, and I know we didn't get through many problems or really any problems in Chapter 11. So what I'd like to do is start out by showing you how to solve a few problems from Chapter 11. And then once we get through a few of those that I think are a reasonable sample, then we'll go ahead and open up the floor to questions about anything from any of the chapters. Does that sound fair? All right, so 11.1 seems like a good place to start. Very first problem, Chapter 11. You're given the voltage and the current as functions of time, and you're asked to find the instantaneous and the average power. And so, of course, we know what is the formula for instantaneous power. Yep, so it's just the product of the voltage and the current. So P, I'll just call it INST. The instantaneous power is going to equal V of t times I of t. Okay? And so here, if we just take these two and multiply them together, we might want to first, actually, is it cosine or is it sine? It's sine right here. We want to get them both into a cosine form, so that way we can use one of our trig identities to be able to multiply these things together. So before I do anything with multiplying V of t and I of t, I'm going to go ahead and manipulate my I of t. I want to get rid of this negative right here. How can I get rid of the negative? Add 180 degrees to my phase. So this becomes 33 sine of 50t minus 30 degrees plus 180 degrees. You can do just the same. Subtracting 180 degrees doesn't really matter. You end up the same side of the unit circle. So at this point we have 33 sine of 50t plus 150 degrees. Now, how can I convert sine into cosine? Subtract 90 degrees. So this is 33 sine of 50t. If I take 90 off of this, I just get plus 60 degrees. Cosine. All right. So now, I'm going to take those and multiply them together. So my V of t, 160 cosine of 50t times 33 cosine of 50t plus 60 degrees. And what did we learn about in this chapter? Maybe we're reminded of in terms of how to do a cosine of A times cosine of B. What did that become? Anybody remember? You could multiply from phasor form, or if you just remembered from the trig identity, let me find the page in your book that is on, early on in chapter 11, you have right here, equation 11.4 says if you have a cosine of A times cosine of B, that equals 1/2 times the cosine of A minus B plus the cosine of A plus B. And so in this case, we'll just call this A, and we'll call this B. And so now, as we're multiplying these things together, we can pull out the 33 times 160. So P instantaneous is going to equal 160 times 33, and that works out to be 5,280, number of feet in a mile, coincidentally, times cosine of 50t times cosine of 50t plus 60 degrees. And so now, if this becomes our A, this becomes our B. This equals 5,280 times 1/2 cosine of the difference between these, 50t minus 50t plus 60 degrees becomes minus 60 degrees, plus cosine of the sum of these, 100t plus 60 degrees. And so now we can just multiply this 1/2 there. We get 2640 times the cosine of minus 60 degrees. Anybody remember what the cosine of minus 60 is? One half. Let's remember where that is in the unit circle. Okay, so if you're, here's our quadrant. If this is minus 60 degrees, our adjacent side is going to be there over the hypotenuse. If we make this kind of a 2-unit circle, remember we have this. This is going to be our square root of 3 side. This is going to be our 1 side. So cosine of negative 60 degrees is just 1/2. Everybody good with that? So we're going to replace this with 1/2 right in here. Plus cosine of, we'll just leave this all the same. And so if you distribute this on through, this just gets divided in half again, so you get 1320 plus 2640 cosine of 100t plus 60 degrees. Okay? So that is our instantaneous power. And now if we want to, of course you could have done this by converting to phasor form and then multiplying things together, adding them together. But eventually you'd have to get back, and so you can just use these trig identities. Now we want to know what is our average power. And so here, average power is what? What's the formula there? Anybody remember? Could be, could be. What I'm thinking is 1/2 Vm Im cosine theta v minus theta I. Remember that? And so, what do we know about our I and our V? Let's go ahead and plug in what we know. We know 1/2. What's our Vm? Comes from the V of t. 160, yep. What's our Im? Now, if I go back to the initial I could say negative 33, but if I want to use this as my theta I, because it's now in cosine form, I'm going to use just 33 right here. And then that way, with my cosine, now all my thetas are relative to cosine functions with positive amplitudes. Okay? And so now, what is my theta v? Do I have any phase offset right there? 0 minus 60 degrees. And so, if you multiply this out, this becomes 80 times 33. That works out to 2640 times the cosine of negative 60 degrees, which we already figured out up there. It's 1/2. So this just becomes 1320 units watts. This should be watts as well up here. Any questions on 11.1? Pretty straightforward. Kind of gets your feet wet with calculating power. All right. Any questions at all on that problem? All right. Now let's move on to 11.3. In 11.3, what we have is a voltage source, and then we've got two loads in parallel. Effectively, it's got one load on it, but you can treat them in parallel, because if we think about power, remember, effectively, we talked about in my class, everything is really a parallel load. So if you plug in your house a washing machine and a curling iron and a television and a microwave, all of those things are loads that are acting in parallel to the power grid, parallel to the power coming into your house. And so in this case, we have a voltage source, 160 phasor, 30 degrees, and you have a 60 ohm load, completely resistive load in parallel with a 90 microfarad capacitor. And you are asked to find, in this problem, the power dissipated by the total load, I believe. Let's look at that. Problem 11.3 says, a load consists of a 60 ohm resistor in parallel with a 90 microfarad capacitor if the load is connected to a voltage source of 160 cosine of 2000 t. So Vs is equal to 160 cosine of 2000 t. Okay, so we know that. I just went ahead and converted it to phasor notation right there for us. So we know that. Find the average power. Okay, the average power delivered to the load. Well, the load is both of these. So there's a few approaches you could take here. The first approach, which actually is a little bit longer approach, is to go about figuring out what is the impedance equivalent of those two loads in parallel to one another. And that's always a way that you can go, is you can always say, okay, let me figure out what all these things add up to be in parallel just using that reciprocal relationship. So you could figure out ZR is just going to equal 60 ohms. And then ZC is going to equal 1 over j omega c, which in this case, omega is 2000. So this is going to be 1 over j times 2000 times c, which is 90 times, that looks like a 4, that's a 9, times 10 to the negative 6th farads. And you multiply all that out, and then you do this whole parallel equivalence kind of thing and figure out what is my equivalent parallel impedance. That ends up going through an adventure of complex mathematics and all those kind of things. What you might want to do other than that is consider, because these are in parallel, you're going to have the same voltage across each of those branches, and one of them is purely resistive, the other is purely capacitive. And what do we know about the phases of those two things? How is the current going to be here? In phase, out of phase, how much out of phase? It's going to be in phase with the voltage. What do we know about the phase here? 90 degrees out of phase. And so if you have a purely capacitive load, how much average power is delivered to it? Zero. because it ends up being 90 degrees out of phase. We'll see that mathematically in a moment. If you have this, it's completely in phase, so all you really have to do to figure out the current is just divide the voltage by the resistance that you have there. So let's go ahead and go through that math. What I'm effectively going to do, instead of doing this parallel equivalence, I'm just going to call this I1 and this one I2. And I'm going to treat this as basically two different problems. I'm going to figure out what is the power delivered on average to the 60 ohm resistor. I'm going to figure out what is the power delivered on average to the 90 microfarad capacitor. And then I'm just going to add them together. Okay? And so if I do that, my I1, that's going to be the current through the 60 ohm resistor, is just going to be the voltage divided by 60 ohms. And so, therefore, my current simply works out to be 160 over 60 in there, and I'm still with a 0 degree offset. So 160 over 60 works out to be 16 over 6, 8 over 3, or about 2 2/3. Okay? Now, my I2, I'm still going to use this. So I'm going to get down to here and I'm going to figure out that this, once I multiply all this out, works out to be negative 100 over 18 J ohms. Once you multiply all that out and take care of the fact that you have a 10 to the negative 6 down there, and you balance that out with this, the impedance of just your capacitor works out to be negative 100 over 18 J ohms. Because I did the whole multiply by J over J, becomes a negative 1 in the top, gets the J out of the denominator. That's what that works out to be. And so, if I want to figure out my I2, I2 is going to equal the same voltage divided by this right here, which is going to be negative 100 over 18 J. And so, if I want to figure that out, this actually works out to be 28.8 negative 90 degrees. How did I get that? Well, if I look at just the magnitude of this, convert this into a phasor, where is my negative 100 over 18 going to be? Think about my unit circle again. It's all multiplied in the negative J, so I've just got a magnitude of 100 over 18, and it's all going down, so my angle, negative 90 degrees. Okay? And so, in this case, this is going to work out to be, I have this angle right in there. Now, once I divide that, that should come out to be positive 90. This is going to be, here, let me show you the intermediate step. That'll be simpler. Everybody see that? That's the phasor for that. Okay? This is the same thing as the amplitude. I could work out the whole square root, but it's going to be square root of 0 squared plus that squared. So it's just 100 over 18 minus 90. When I go about dividing this, this becomes 160 times 18 divided by 100, phasor 90 degrees. Everybody good with that? And so, let's go about figuring out our average power. So the power at the 60 ohm resistor is going to be, now this is where we're going to go back to the phasor and the real part. 1/2 of the real part of our voltage phasor. It's going to be 160, 0 degrees, times our current phasor, 8/3, 0 degrees. All right. As it turns out, that's all real, right? Because we have 0 degrees. So this is 1/2 of the real part of the voltage phasor times the current phasor. So this is the voltage and this is the current through the 60 ohm. So that just works out to be 1/2 of the real part of 160 times 8/3, which is really just 1/2 of 60 times 8/3. So that works out to be 213 1/3 watts. That's the power dissipated by the 60 ohm resistor on average. Now, the power at the 90 microfarad capacitor, use the same formula, 1/2 of the real part of same voltage, 160 phasor 0, times, let's go back to this. This works out to be, this by the way is 28.8, 90 degrees. 28.8 times 90 degrees. All right, so we can go ahead and multiply those two phasors together. So this is going to be 1/2 the real part of, what's 160 times 28.8? 4,608. And what's my angle going to be? 90 degrees. Now, let's go ahead and figure out what this is. Yes, Tony.
So what's the difference between the I and like the I star? I know it's like the complex conjugate.
That's the conjugate transpose.
Right.
Okay? So what you're going to do when you have the I star, and actually that's what we should have done here.
Yeah.
So let me fix that right there. So this is our I. All I need to do for I star is make this a negative angle.
Okay.
Let me fix that real quick. There you go. As it turns out, the cosine of 90 and cosine of negative 90 is the same, so mathematically it'll work out the same. But yeah, when you need to do the conjugate transpose, all you need to do is put a negative right there. Griffin.
Can you raise the board just a little bit?
Yep.
Thank you.
Yep. James.
Back up above where you had it as negative 90 before,
Yep.
how did you get from negative 90 to regular 90? Did you do a conjugate there? Is that how you?
When I divide these, I end up subtracting
Right.
this minus this, so 0 minus negative 90 becomes positive 90. This is my voltage. This is my
0
current.
minus, that makes sense. Okay.
So I end up with a positive 90 because when you divide these two and you subtract the
Right.
phase shifts. So that's how I got that. So now I've got this. This should be negative 90. And so now let's go ahead and put this back in terms of a complex pair and figure out what the real part is. So if we take this phasor, this works out to be 4608 cosine of negative 90 degrees plus 4608 J sine of negative 90 degrees. All right, kind of ran out of boardroom. What does this work out to be? Cosine of negative 90? That's 0. This whole term goes to 0. What does this go to be? Sine of negative 90 is negative 1. So I end up with negative 4608J. That's all I have inside of there. What's the real part of negative 4608J?
None.
0. So this whole thing goes to 0. So the average power delivered to the 90 microfarad capacitor is 0 watts.
Is that what you were saying like earlier with a purely capacitive system?
Mhm.
It's just 0?
Yep. So when I go back to what I actually had here, a purely capacitive load on average dissipates no energy. Why? Because effectively when you have AC, you have this charging, discharging, charging, discharging. And all of your currents and all of your voltages basically balance out. You give it charge, and it gives it right back. You give it charge, and it gives it right back. And so when we're talking about power being dissipated, power is really only dissipated when you have resistive loads. Now, it's very rare to have something that is truly 100% capacitive, as we talked about. So even if you have a capacitor, there's still some resistance in the leads on the capacitor. There's oftentimes some kind of wire going in there. You've got to plug it into a wall, so it's got to get energy somehow. But in this case, because this is an ideal textbook problem, we're going to say this is just capacitive on there. This is just resistive. So now, let me finish this up. The power dissipated by the load, on average, is just going to be this plus that. So we're going to add that up. This turned out to be 0. Power dissipated there turned out to be 213 1/3 watts. So the total power dissipated on average is just 213 1/3 watts. Yes, James?
So back to your water bucket imagery, when it's that capacitor like that and it's at a perfect 90, the amount that it puts in is the same amount it sucks back out in that opposite direction.
Yep. So effectively, in my class, I've talked about a capacitor is basically a charge bucket. And so as you're filling up the charge bucket, in DC world, it fills up, then it stops, and it holds on to it. It can't hold any more charge. And then at some point, when you cut off the DC, it throws that back on the circuit. In AC land, effectively what I have happening is fill up the bucket, okay, and now I'm going back the other way, bucket's pouring back out. Fill up the bucket, okay, and then the bucket is pouring back out. So you constantly have a filling, pouring out, filling, pouring out in typically a sinusoidal fashion. Yes, Thomas?
Can you explain how it goes to 0 on the bottom right corner?
Yep. Where are you tracking to? Do you understand this?
Yes, sir. It's at the very end, because the brackets got mixed up, and I was trying to catch
Okay, sorry. So in this case, I've got my voltage phasor, conjugate transpose of the current, which I got just by throwing in the negative 90, or the negative sign right there. Multiplied those out. Multiply the two magnitudes, add the two phases. So I get this. And then what I need to do is just get this back into complex pair. So I take this, multiply by cosine of that, cosine of negative 90, 0, plus this times j times sine of negative 90. And so this cosine of negative 90, that went to 0. This part right here, I end up with negative 4,608j. But what I'm looking for is the real part of that. All I end up with is an imaginary component. I have 0 real component. And so this is my real component at 0. The entire real portion of everything in the bracket is just 0. All right? And that's because this was purely capacitive. It would be the same, but an opposite sign if it was purely inductive. If I had a purely inductive load over here, then my phase angle would just be the opposite sign, SIGN sign, but it would still work out. The real component would still be 0. So if you ever are given a problem where you have multiple things in parallel like this, if those branches are purely resistive or purely capacitive, here's a nice shortcut you can take. Anything that's purely capacitive or purely inductive is going to, on average, dissipate 0 power. Anything that's resistive, if you just want to find the parallel equivalent of all the resistances, you can do this the same exact way, just one time. Okay, so there's a nice little shortcut you can do to find the average power of a bunch of things in parallel. So if you ever see this and you're asked, okay, how much power is dissipated right there on average? 0. Don't even have to do math. We did the math to show that, but that's going to be true every time you have a capacitor just by itself or an inductor just by itself.
What other tricks do you know?
I don't have enough time to tell you all those. You got to come back next semester.
So if there's a capacitor and an inductor and a resistor, you'd have to do the math for all three of them, right?
Well,
You know, like-
if I had this, let's say I extended this on out. I had an R1, had an R2, had C1, C2, and an inductor over here, and I ask you, find the average power dissipated by that whole mess. This one's 0, this one's 0, this one's 0. If you want to just do a parallel equivalent of R1 and R2, then you can just do that for one branch, just looking at those in equivalence. You could, of course, do all this out, but I'm going to tell you, the real portion is going to go to 0 every time. So save yourself some time and just keep that trick in your back pocket and go, I know what this is. Boom, 0.
Thank you.
All right. Yeah.
Okay, so the last problem and this problem, we found average power for both of them, but we used two different equations. When do you use which one?
Okay. The reason that I use it, you could really just do the same thing here when you're doing the average. I just went back to this because it was largely given in the time domain.
Okay.
Since I was already given,
That's the time that was.
yeah, I was already given the current in the time domain on the other one, so I just used that.
Okay.
But in this case, yeah, it was pretty easy to go back and do it as a phasor. I could certainly redo the average with phasor mathematics on problem 1. Then you have to remember to do the conjugate transpose with the phasor, which I, of course, forgot in there. Mathematically, it still worked out. Negative 90, plus 90. James is shaking his head at my forgetting to put a negative sign in there.
How could you?
I apologize. All right. Let's keep going. 11, 13, pretty easy problem. So in this case, we're going back to Thevenin equivalence. And you're told in 11:13, the Thevenin impedance of a source is, let's find this. This is 11:13. ZTH is 120 plus J60 ohms. And the peak Thevenin voltage, VTH, is 165 plus J0 volts. Okay, so we're given that as, this is not a decimal, 165 J0. So all real there. And so then we're asked to determine the maximum available average power from the source. Now, if we remember the derivation that we did on Tuesday in class, Allie, sorry you weren't here for all the fun calculus, partial derivatives and all that.
It was horrifying.
It was quite splendid, if I do say so myself. What we want for our load is going to be, for maximum power transfer, RTH minus XTHJ. Everybody remember that? So it's effectively the complex conjugate of the Thevenin impedance. That's where we get our maximum ZL for max power transfer. And what we did was we plugged this in and we tried to figure out what would be the maximum power. And it was actually worked out It's derived in your book, but from equation 11.20 in your book, the maximum power on average that you can get is equal to the magnitude of VTH squared divided by 8 times RTH. And that really comes from basically treating this as a voltage divider. Everybody remember that? We treated this as a voltage divider. Here's your Thevenin voltage. Here you can sort of, I'm drawing this as a resistor, but of course it's complex. So it could be a resistor and capacitor pair, resistor inductor pair. So this is your ZTH. And then here, this is your ZL. And this is going to be RTH plus XTHJ. This, for max power, should be RTH minus XTHJ. And if you set that way, the maximum power that you will dissipate works out to be just this. And so if you simply plug in the numbers that you have, VTH, 165. So in this case, this is the magnitude of that. If you had an imaginary part, you would have to do the whole square root of the real part squared plus the imaginary part squared. They were nice to us in the book and just gave us a 0 there. So it's just 165 quantity squared divided by 8 times our RTH. That's just the real part there. So that's the 120. And so when you do that math out, that works out to be 28.36 units watts. Don't it?
Could you give us an example where it's not 0?
Okay. So if I did VTH was 165 plus J4. Okay. So now what I would do here is instead of 165, this would be square root of 165 squared plus 4 squared. Quantity squared. That would be my magnitude of VTH.
So
How do
the
we
power
get?
is just the real part, right?
What's that?
The RTH is just the real part.
Yep. Yeah, because this RTH is the real, and this is your XTH. So you have resistance and you have reactance. The reactance is the complex part. The resistance is the real part. So that's really the major thing when we're talking about doing these things in AC and we have the complex pairs, is you just have a real part and you have an imaginary part. And in a lot of cases, we're mostly interested in the real part. Okay? That's what power factor correction is all about, is trying to get real power out of things. Okay. Any questions on 1113? All right. Then let's go on over to 1125. This is kind of a fun little problem. So in this case, you're asked to find the RMS value of a signal. And you have kind of this weird little stair-step signal. Who can tell me what the purpose of RMS is? Why do we care about the root mean square? If I'm thinking about a VRMS, why would I ever want to compute that? So what that effectively is if I'm trying to figure out how much power, let's say a sinusoid, is delivering. When I find the RMS, that is effectively the signal. If I just held a constant DC voltage at the RMS value, I would deliver the same average power over time. Okay? So in this case, if you remember, when I had a sinusoid, at its peak, I have a maximum positive power being delivered, typically. At the bottom of the trough, we can sometimes even have a negative power being delivered. Everybody remember that? And so if I figure out the RMS, which is effectively thinking about the average effect of that signal, it might be somewhere in there. And so if I figure out the RMS voltage and the RMS current, that is on average what this would behave like if it were just a DC source. Okay? So then we can go back to simpler mathematics. We effectively eliminate the need for calculus because we'll do the calculus once, and then to figure out the average, we'll just use that value that we've solved for with the calculus. Okay, so in 1125, what you're given is a funny looking signal that looks something over time like this. You've got a stair step, and you got this, then it stays here, then it goes up, and then it goes back down. And then it stair steps, it stays here, it goes up, and presumably it just repeats this pattern over and over again until the end of time. And let me make sure I give you the right magnitudes on this. This goes up to 10 and down to -10. Okay. This is just given as some kind of an X signal. We don't really know if this is a voltage or a current or what it happens to be. We're just asked to find the RMS of the signal. And we know there's an equation that we're given. X RMS is equal to the square root of 1 over the period integral from 0 to that period of x squared dt. Oh, let me also give you time units. So each of these steps happens in basically 1 second intervals. Okay? What is the period of this signal?
3 seconds.
3 seconds. And so the full period of this is going to be over 3. So I'm going to plug that in for my t. And effectively, I don't have a continuous function in here, do I? So what I'm going to do is integrate it piecewise. I'm going to integrate it. I'm going to start here at 0 and integrate to 1. I'm going to integrate 1 to 2, and then I'm going to integrate 2 to 3. Is that okay? And so I'm going to plug in square root. I can still do 1 over the whole period. My whole period's 3. And then I'm going to multiply that. I'm going to integrate from 0 to 1. What is my function from 0 to 1? -10. So I've got to do -10 quantity squared dt plus integral from 1 to 2. What's my function from 1 to 2? 0 squared dt. Here, let me throw this a little higher so you guys can see it. All right. Plus integral from 2 to 3. What am I from 2 to 3? 10. dt. All right, so now I'm just going to finish this up over here, if that's all right. I'm going to say x RMS is equal to square root of 1/3 times, what is the integral of this going to be? 100. The integral of it will be 100t. Okay, so 100t evaluated 0 to 1 plus, what's the integral of 0? 0 plus, this also will be 100t evaluated between 2 and 3. And so if I plug this in, I get square root of 1/3 times, that works out to be 100 plus 0 plus another 100. So this works out to be square root of 200 divided by 3, or if I factor 100 out of there, 10 square root of 2/3. And if you don't like square roots of fractions, that works out to be approximately 8.165. James.
So even though it's a negative voltage, it's still producing a positive power.
Yep. Yep. On average. So at that point, yep.
Right.
Yep. Well, because at that point, you may have a negative voltage and a negative current. So when those end up being multiplied together, negative times negative becomes a positive.
Positive, right.
Mm-hmm. Griff.
So this kind of like with the problems we had like in the first chapter where we would analyze a graph of like power and like what it's doing
Mhm.
in between each stage.
Yep.
Just a little more complicated.
Yep. Yep. Yeah, and really, you know, we could have just done this completely graphically, but to get the RMS, it's not analyzing the integral of this graph, it's analyzing the integral of the square of that graph. So we could have just redrawn it as the square, in which case each of these would go up to positive 100, positive 100, things like that. Okay. Riley.
What's XRMS again?
XRMS is the root mean square. So this effectively, if I were to use this, if this were, let's say, a voltage, and I were to use it to drive some kind of a load over here, I might have a voltage that looks like this. The RMS of that signal is effectively what DC value over time on average would deliver the same power to the load.
So with the X, is that just saying it could be?
It could be a current, it could be a voltage, whatever it happens to be. So X is just their generic.
Okay, for anything.
It's a current, it's a voltage, it's a whatever it happens to be. All right. Any questions on 1125? Let me go through one more of these RMS things, and then I'll get into briefly power factor correction, and then I'll open it up for you guys. Okay? So 1127 is very similar, but it's a different shape signal. So in 1127, what you're given is kind of this funky looking sawtooth triangle wave kind of thing. So in 1127, you're given, this you're told is a current. And so here it peaks at 5, and you're given here's a 5. So every 5 seconds, presumably, you end up having this kind of right triangle looking pattern. And so you're asked to find IRMS. This is a current. So how do we go about doing that? Same way we did before, right? So the IRMS is going to equal square root of 1 over the period times integral from 0 to the period of I squared dt. What's one period here?
0 to 5.
Yeah, so 5 seconds, presumably. They didn't tell us the units were seconds. I'm going to assume it's seconds. Riley, yes?
Could we, I guess, take the area of one of the triangles, multiply it by how many triangles there are, and divide by 2 for the average? Or would that not work for this?
In this case, well, you can't just take the area of the triangle because we're really taking the area of the triangle squared. If you could redraw this as the triangle squared, yes. Okay? But we're not integrating just this signal, we're integrating the square of the signal. That's the very big important thing to note when you're doing RMS. And these are actually supposed to be going up the same peak. I don't know why I trailed off, but they are consistent. Okay? All right, so now what we need to really do is figure out what is our expression for I of t. So we can plunk that into the integral. What is it from here to there? Don't worry about the fact that it drops off. What does that look like?
A ramp function?
It's a ramp function. It's pretty much, let's go back to algebra 1.
Just equal to x.
What's the equation of this line?
Just x, right?
Or
Y equals x. I mean,
t.
or, yeah, y equals t.
Okay. I of t equals t from 0 to 5. Everybody good with that? So, if we go in here, 1 period is 5, so this becomes 1 over 5 integral from 0 to 5 of t squared dt. So this is going to be square root of 1/5. What is the integral of t squared? 1/3 t cubed, or t cubed over 3. Evaluated between 0 and 5. So this is going to be square root of 1/5 times 25 to the 3rd over 3 minus 0. And so my 25 to the 3rd I can divide by 5, and I just get, wait, why did I do that? 5 to the 3rd, sorry. I already did the squared in my head. I got one step ahead in my head. 5 to the 3rd divided by 3, so that just becomes square root of 5 to the 3rd divided by 5 gives me 25 over 3. And if you want to, you can go ahead and take the square root of the numerator and the denominator. That goes to 5 over the square root of 3, or that equals 2.887 units amps. Any questions on that? Yes, John.
My question is back on 1125. So
Uh-huh.
I see how you got the period where t equals 5 on 1127. How did you get 3 on 1125?
How did I get 3? Because the period is basically saying if I have a repetitive pattern, how long does that repetitive pattern last? You know, it goes over and over and over again. So if I look at my repetitive pattern, I see that I have a negative 10 from 0 to 1, I have a 0 from 1 to 2, and then I have a positive 10 from 2 to 3, and it's doing that over and over and over again until the end of time. And so that whole repetitive pattern takes 3 seconds, and so that's my full period there. Just like, you know, a lot of times we only think about periods in terms of sinusoids. We're so used to thinking about the period just being here, right? But now, for RMS, we're more generically thinking about what's the period of any particular signal. If I have a repetitive pattern, how long does it take for that one instance of that pattern to happen? In this case, it's this triangle and fall off. In this case, it's this sort of stair-step looking function. That's what we have there. All right. One last problem, and then I'll open it up to the floor for questions. This last problem gets into complex power and power factor correction, which I think is important to do. So if we go on to problem 11.39. You're told you have an AC motor, and in that AC motor, the impedance is 2 plus J times 1.2 ohms, and it's driven by a source that is 220 volts and 60 hertz. Okay, and it's a sine wave. So this is basically what you're going to see coming out of something like the power outlet you might have for a dryer in your house. So these outlets typically are about 110 to 120, but if you have a dryer outlet or something like that, some people's hot water heaters go into a higher voltage source. That's about what you're going to see right there. Okay, and so we have a motor being driven by that. We're asked to find a few different things. Find the power factor, P, Q, and find a capacitor that will correct PF to unity. And unity means 1. Okay, we want it corrected to unity. All right, so what we can do is go ahead and find the RMS values of these things. So my VRMS, if we know this is a sinusoid, what is the RMS? Anybody remember? Works out to the peak divided by what? What's that? Not 0. Close? Square root of 2. So VRMS 220 divided by square root of 2 volts. Okay, so if you're trying to find the RMS of a sinusoid that does not have a DC offset, 220 in this case, amplitude divided by square root of 2. Now let's go ahead and find our current value. And so in this case, our I, not our IRMS, we'll get back to that in a little bit. That's going to equal, if we draw this, effectively we have a voltage source and we have an impedance. And we want to figure out the current. I going there. So we take our voltage, I can convert that to a phasor. No offset. Divide it by the impedance. 2 plus J1.2. I'm going to go ahead and convert this impedance into a phasor. How do I do that? All right, so what is the magnitude of that phasor? Square root of 2 squared plus 1.2 squared. And then my angle here is what? Inverse tangent of the imaginary part divided by the real part. Okay? And if you do that out, that works out to be 2.332, 30.963 degrees. Okay? So that's our I. Now we can go ahead and divide these two phasors. Divide the magnitudes there. So 220 over 2.332 works out to be 94.3396. And just subtract the angles. So you get a negative 30.963 degrees. Now what I can do, This is still going to be a sinusoid. I can find IRMS. So IRMS is just going to equal this amplitude, what? Over square root of 2. All right. And so now, what I'm going to do is I'll find S. Let me throw this up, throw this down. So S is going to help me figure out my P and my Q. So S here is equal to the magnitude of VRMS. I don't know why I wrote that small. VRMS times the magnitude of IRMS times, well, actually, I can write it as a phasor. I'll write it that way, and then it becomes theta V minus theta I. Okay? And so, if I go ahead and do this out, what is my theta V? 0. I had no phase offset. What's my theta I?
30.963.
Negative 30.963. So this angle becomes positive 30.963 degrees. VRMS times IRMS, just multiply those two together. That works out to be 10,377.36. All right, so now let's start answering the actual questions. The P turns out to be the real part of this, and the Q turns out to be the imaginary part of this.
What are the things?
What's that?
What is the real power?
The P is the real power, and the Q is the quadrature power. That's the imaginary. Okay? And what we ultimately want, the power factor, is going to help us understand the ratio with our total power. So this S is our total power, and that's made up of a real and an imaginary component. In an ideal world, all of our power would be real, so that we're actually transferring real work to a real load. Okay? But because we have complex loads in here, we actually end up with some imaginary portions of our power. That doesn't do any work for us, and it just drives up our bill. Okay? So what we're ultimately going to do in part B is we're going to pick a capacitor to put in parallel that will shift that vector so that we ultimately get to a power factor of 1. Griffin.
So wait, where's your VRMS and IRMS come from? The IRMS is the 94.3396, right?
Mm-hmm.
And then which one's is the VRMS?
Or sorry, it's the 94.3396 divided by root 2.
Okay.
So this 94.3396, if I were to do that in the time domain, that's my amplitude. I just divide that by square root of 2. That gets my RMS value.
Okay.
Allie, did you have a question? Okay. All right. So now what we need to do is say P is going to equal the real part of S right in here. So that's the real part of 10,377.36 cosine of this angle, 30.963, plus J times 10,377.36 sine of 30.963. All right. Now, of course, this is your real part. This is your imaginary part. Q is equal to the imaginary part of that. I'm not going to redraw it on the board. And so what P works out to be is $8898.58. Q works out to be 5338.99. And I am different by a factor of 2 with the answer in the back of your book, and I have no idea where that went to. I'm pretty sure I did this right, because I redid it a lot of different times. So your P's and your Q's, those are off by a factor of 2 compared to the answer in the back of the book. So, but that's basically how you do that. And then the power factor, PF, is just equal to the cosine of the difference in angle between your voltage and your current. So that's just going to be cosine of 0 degrees minus a negative 30. So that's plus 30.963 degrees. And so that works out to just be 0.8575. So that's your power factor. Now, in an ideal world, we want our power factor to be unity, meaning 1. Okay? Unity is a good word to know, especially if you're going to be a double E. When people say unity gain, they mean gain of 1. So get in the habit of understanding the word unity. In this case, not ideal. Okay? So we've got 0.85. So what can we do? Well, we can add a capacitor in parallel to this load. So effectively what happens is you've got an impedance right now as your load, which is modeled as effectively an inductance and a resistance in series. This is basically what you have. You have some sinusoid. So sometimes voltage sources are drawn like that. A lot of times if it's AC, we draw it like that. If it's DC, we do a little plus minus. So you have this, and effectively right now, your load has some real part and some imaginary part, typically modeled as an inductance. Most loads, if you think across a broad power grid, will end up being inductive and resistance. Inductance largely comes because there's a lot of things that rely on motors. Think about your washing machines, your dryers, a lot of mixers, all those different things. There's a lot of inductors in what we're dealing with. And what we can do to change that power factor is we can pick a capacitance to put in parallel there. And effectively what we're doing is we're picking a capacitance so that ultimately we nullify the effect of this inductance. And what that does is it really just adds a vector to kind of bring this power from something that is away from the real axis. So right now we've got a power vector that looks like that, and now we're trying to shift this upward so that it now looks like it's mostly real. If you ended up with a real and capacitive load, which is possible but rare, what you would do is add an inductor out here. Ultimately, what we want is our resultant vector to have the same real component and to eliminate the imaginary component. That's what we're trying to do by picking a capacitor. And what you were told in your book is that you can pick a capacitor. There's a derivation of this in your book. I'm not going to, in the interest of time, go through it, but I would recommend you read the derivation of it. If you want to go from some angle, right now theta 1 is where you are currently, to where you want to be is theta 2, then you can pick a capacitor as P times tangent theta 1 minus tangent theta 2. That's the angle you want to get toward after your correction, divided by omega times V RMS squared. Okay? That's ultimately what you want to choose to get to an angle theta. What angle theta do we want? We want 0, so we have unity gain. So theta 2 is equal to 0. What is our theta now? Theta now is this 30.963 degrees. What is our p-value? We just solved that. That's the real part of this whole thing. So P is equal to 98.58. Our omega, if we go back to our source, 2 pi times 60. We're given F. Omega is equal to 2 pi times F. So that's going to be 2 pi times 60 hertz. So it's basically 120 pi, or approximately 377. We were given that our source here driving the load is at 60 hertz. So that's an F value, and I just multiply that by 2 pi to get to an angular frequency. All right, so that's my omega value. And then my RMS, I already put in as 220 divided by square root of 2. And so if you plug all of those values into that formula, it works out to 585 microfarad. And so that would be the capacitor you would pick to put out there. Any questions on that? So that was kind of my semi-high speed hour and 11-minute journey through chapter 11 problems. Yeah.
Is the S complex power, or is it the like? I know there's like S and there's like S like bolded.
Right.
What's the difference between those?
So the S here is the, yeah, I think that's your apparent power.
Apparent power.
Yeah.
Okay.
Actually, no, I'm sorry. This S is your complex power. So the complex power is that the non-bolded S, that is your apparent power. That's just the magnitude of bolded S.
So this is
Okay.
So this S that we solved for here, this would be bolded. I don't have a bold chalk, but that would be your bolded S. And so that is your complex power. If you want to get to the apparent power, it's just the magnitude of this. So you could go about just doing square roots of angles and such. Real component, imaginary component, all that. James.
On tomorrow's test, how many cheat sheets are we allowed to have?
You're allowed to have 2 sheets of paper, front and back, whatever you
I
want.
take glue and glue 2 pages back to back so that they're better looking. Can I do that twice?
So long as it looks like you just have, that's fine. I don't care how thick they are or if there's an adhesive between them.
But you don't care how thick they are.
I feel like a loophole.
We do this as a thing, Doug.
It's not a cube. It's not going to be a cube,
We
okay?
can make a cube.
No,
Can we
How
have
many questions are going to be on it?
I don't know.
4 sheets of questions?
Have you made
So what now?
I made a test 2 years ago. I'm going to look at that and see if I like it. And I'll always modify it. So, yeah. Yeah. I mean, it'll be longer because you guys have 2.5 hours as opposed to 50 minutes.
So it's going to be similar to the first two, as in
Yeah.
that material that we've covered.
Yeah.
And then the
So it is comprehensive, so you'll have things going back to find an equivalent resistance with all these parallel series combinations, find equivalent capacitance, inductance, nodal analysis, mesh. In a lot of cases, I might not have you solve the whole problem. I'll say set up the equation or tell me what the power is here, those kind of things. Maybe like I've done before on this last quiz, I don't ask you to do all the superpositioning, but show me the circuits that you would use to analyze to do superpositioning. I don't want it to be an algebra test or a Diffie-Q test. You guys have other classes that teach you those things. But you need to know how to use those tools to get to where you need to be. A lot of EE, you'd plunk stuff into MATLAB. It'll do the work. You need to know what needs to be plunked into MATLAB, and that's what I'm trying to test you on. Yes, Griff.
How similar are some of the questions going to be, like the homework ones? Because there's some like really like weird homework questions that I don't know.
Is it gonna be quiz level or is it gonna be level out level?
So here's my general rule of thumb. I always take my own tests before I give them to you, and I try to give you at least 4 times as long as it takes me.
Okay.
So I'm only going to ask you stuff that I can do in about 40 minutes because you have 2.5 hours. Okay? So I'm not going to ask you to do a huge derivation that's like a 3-page homework problem. It's going to fit on a page. Almost anything I ask you to do, you can fit on 1 sheet of paper. Okay? I usually give you enough space to work it out. You guys have seen what I've asked you on other tests before. Well, you haven't, but if you want to see my previous test, you can.
Much nicer than ours. There's less like competition, I guess.
Yeah.
It's more like, do you know how to set up this and just
I don't teach math classes, I just use them.
Could you rework one of the problems from the quizzes?
Yeah, which one do you want to see?
It's problem 2 on quiz 5.
Let me see, did I bring the quizzes with me to get back?
Was that, which quiz was that? Quiz 5?
So that was the RC section.
It was when we had like the GBT.
Oh.
Let me hand these back too. Here's your quiz 7s that we just.
So these are gonna be the same kind of problems that you had on the test and the quizzes, same.
I didn't reinvent circuits just for the final exam. I mean, every.
There's not the new unit that
No.
we're talking about. Hey, company
You've never seen this before.
Would you mind if we did 4 front sheets of paper so they don't bleed through?
That's fine.
That's on
Pick up like ours was for 2 pieces of paper, but 2 front tabs.
Yeah. I would ask.
Up here, the real value, 8898.50.
Like you see how you
Yeah, it's the real part of that, so it works out to be the 10,377.36 cosine of 30.963 degrees. And then the Q is what's multiplied by the J. So the Q comes from the imaginary part, the P comes from the real part.
when you like D equals RE.
RE just means the real portion of this. IM means the imaginary portion of this. And so I got lazy and I didn't want to write out the whole thing again. I just said it's the imaginary part of that thing within brackets. That's what I just went through, is any of that stuff. So you need to know from chapter 11 things like, why is there a power factor correction? Why is that important? How do you compute your S's? How do you compute instantaneous and apparent power? All that kind of stuff.
On the quiz here, you have a note that says no. Is that to the units or is that to the problem? I'm assuming it's to the quiz.
If you have a specific question about how I graded something, let me know and we'll talk about it.
Okay.
Okay. All right, so you wanted to see one of the quiz problems, Tony?
Yes.
What would you like to see?
It's question 2 on quiz 5. I can just give this to you.
Okay.
I just didn't get, like, it just confused me.
All right, let's take a look. So question 2, this is quiz 5. Question 2, and I gave you this circuit here, and this was a 5U of t. You had a 1K, you had a 2K, and then over here, you had a 10 microfarad capacitor, and you were told this is your V, and you were asked to find 6 things. V at 0 minus, V at 0 plus, V at infinity, dV, dt at 0 minus, and dV dt at 0 plus. So let's go about seeing if we can figure that out. Oh, and then you were asked generically to find v of t for t greater than 0. All right, so let's go ahead and look at how we could solve for all of these and make sure we understand what's actually happening. So, to get our voltages or currents or anything like that at 0 minus, what do we do? When t is less than 0, we assume everything is at steady state. And so what steady state do we have here before t equals 0? This is 5u of t. What does that voltage source behave like before t equals 0? 0. And a 0 volt supply looks an awful lot like a short. Okay? So before t equals 0, we've got that. Resistors just kind of hang out and do their thing. They're pretty resilient. They can change current instantly. They can change voltage instantly. What does our capacitor behave like? Open circuit. All right, so at 0 minus, what's our voltage here? 0 volts. There's no supply. Nothing's on. So effectively, we would assume this has behaved like a source-free parallel RC circuit. And over time, the capacitor, any charge on the capacitor, has had enough time just to dissipate. So our V at 0 minus is 0 volts. Now, let's look at what happens at 0 plus. This is where it's a little tricky. Okay, so right here, what do we have? Now, as soon as this turns on, how many volts is that supply? 5 volts. We still have 1,000 ohms here. We still have 2,000 ohms here. Now we have our capacitor. It's tempting to think that's a voltage divider. But what do we know about how capacitors behave with their voltage? They can't change stepwise instantaneously. So V at 0 plus also better be 0 volts. And so what that means for us, a lot of people see this and they know my affinity for voltage dividers and they think, oh, Castles gave us another voltage divider. I tricked you. Okay? I wouldn't dare do that, would I? Well, what does that actually mean? Now we have to go back to our first principles of nodal analysis and look at what's actually happening. We still have 0 volts right here. So therefore, how much voltage is dropped across an element that's in parallel with 0 volts? 0. So therefore, how much current goes through this 2K resistor? None. Uh-oh. And I have 0 volts right here. So now how much current do I have going through the 1K resistor? 5 volts divided by 1,000 ohms, better known by its street name, 5 milliamps. Okay? All right? 5 milliamps. Where does all of that current go? We just said none of it can go here. Now it's all got to go through the capacitor. Capacitors can have a stepwise current change. They cannot have a stepwise voltage change. And so, what does that mean right here? Well, let's do this one first. dV dt tells us something about the current that's flowing here. Remember, I equals C dV dt. And at 0 minus, how how much current do I have flowing through the capacitor? 0 amps. I do have a positive C value, so that means dV dt at 0 minus was equal to 0 volts per second, because I had no current. That is not the case at 0 plus, because right here now I've got 5 milliamps. That is equal to C dV dt at 0 plus. And so here I plug in my value for C, 10 times 10 to the negative 6th. So 5 times 10 to the negative 3 amps equals 10 times 10 to the negative 6th farads dV dt at 0 plus. And so therefore, dV dt at 0 plus is going to equal 5 times 10 to the negative 3 amps divided by 10 times 10 to the negative 6th farads. This works out to be 0.5 times 10 to the third, or 500 volts per second. That makes sense? And then our last part over here, V at infinity, we have to yet again look at what is this going to behave like as t goes to infinity. This is going to be a 5 volt. Now's the time for our old friend, the voltage divider. Because now the capacitor behaves at steady state again like an open circuit. And so this now becomes V equals 5 volts times 2K over 2K plus 1K. 2/3 of 5, so 10/3 volts. Or 3 1/3 volts. So that's our steady state there. And so you can, using these values, you can go ahead and plug into the general steady state form, figure out your VP. That help? The derivatives are really what's tricky on these. And that all comes down to knowing this voltage is not going to change and not being duped into thinking this is a voltage divider. It eventually becomes as such once this gets to steady state, but instantaneously when things are shifting around, you can't get there. Riley.
It's not part of this, but you know how you can combine a resistor and current source and turn it into a voltage resistor?
Mm-hmm. Mm-hmm.
Can you do that with an inductor and a capacitor?
Yep. So if you're talking about doing source transformation, if you have a complex impedance, any kind of Z value, if that is your value, you can basically do source transformation. So you can convert voltage source in parallel with, here, let me show you. This might make sense. So if you have,
So it would only work with like the chapter 9 and 10 stuff.
well, it basically works in general, because chapter 9 and 10 is the same fundamental of what DC works with. It's just omega is 0. And generally, you don't have any complex. So if you have, let's say, a voltage source here, and you have any kind of Z value, that could be capacitance, could be inductance, could be some sort of combination, you can do a source transformation to convert that to an I in parallel with the same Z. And you just make the I equals V over Z. Now, of course, these, if I had an emboldened font, those would be phasors. You just have to do the phasor mathematics.
So I couldn't technically move the inductor over the capacitor if I could only move the impedance value over.
Right. So you can't just do source transformation, inductor, capacitor. It would have to be a voltage source or a current source transformation in there. Thomas.
On test 2, problem 7.
Mhm.
I don't know if you have it or not. But
I don't have it in front of me, but
yeah, a voltage source in series with a resistor and then
Uh-huh.
inductor.
Uh-huh.
And so when it goes to steady state, you should come on the voltage of the inductor, and it's 0, but I'm trying to understand
okay.
why that is.
You want to understand, what were we asked on that? The steady state? Let's go ahead and look at it. Thank you. I'll be right there. Whoop. Appreciate it. All right, so this is problem 7 of test 2. You were given a DC 10 volts, 1 kilo ohm resistor. You had a switch that is closing at t equals 0. And then you had a 1 millihenry inductor, and you're told this is V of t, the voltage across the inductor. And the current, this is I of t. It's just one big serial loop. So you were asked to find V at infinity, and you were asked to find I at infinity. Well, let's think about what this is going to behave like as t goes to infinity. This is going to be a 10 volt source. You're going to have a 1K resistor here. This is now shorted. The switch is now closed. What does an inductor behave like at DC steady state? Short. This is V at infinity. How much voltage gets dropped across a short circuit? 0 volts. And what's the current here? Just 10 volts divided by 1 kilo ohm. 10 milliamps.
I was looking at is the voltage drop.
Yeah, so it's all about recognizing the voltage drop across a short is just 0. John.
Same test, number 1, what was the explanation for that?
I don't remember what problem I asked you. What did it say?
I think number 1 was why do the capacitor circuits often saturate?
Yeah, comparator.
Oh, why do comparator circuits often saturate? Okay, so here's the idea. Oh no, saved it from the hole. Wow, that's how things end up in the hole. So on an op amp, let's remember what the ideal characteristics of an op amp are. So on an op amp, what do we have? We have infinite input impedance or input resistance. So effectively, what you have ideally means there's 0 current here and there's 0 current there. The other thing that you want is if negative feedback, meaning you have something, it could be a resistor, could be a capacitor, could just be a wire, going from your output back to your negative terminal, your inverting terminal, then V plus equals V minus. What's the difference on a comparator circuit? You don't have this. There's no negative feedback. And the other characteristic for an ideal op amp is, what is the ideal gain? Infinite. And so if you don't have negative feedback here, what that means is you have a V plus and a V minus, and the difference between them is multiplied by a gain of infinity. And if this voltage is bigger than that voltage, that multiplication will almost assuredly be bigger than your positive voltage rail. And if this is greater than that, you're going to be multiplying a negative voltage by infinity, and that most assuredly will be lower than your negative voltage rail. And so, because there is no negative feedback, the basic explanation is because comparators lack negative feedback, V plus does not equal V minus. Therefore, VO is driven to infinity times V plus minus V minus, which will be outside voltage rail boundaries. That's the most comprehensive answers. And we exploited that to our gain on the project, right? We wanted to know, is this bigger than this? And what we effectively made those two op-amp comparators do is saturated either the positive rail or the negative rail to indicate this voltage is bigger than that voltage. And one of those was your known voltage from your simulation, whatever voltage you got out at 20 degrees Celsius. The other is whatever you expected to get out at 50 degrees Celsius. And that allowed you, if your voltage was greater than 50, whatever voltage you would get at 50 degrees Celsius, it's saturated. And if it was less than whatever you got at 20 degrees Celsius, it's saturated at the other rail. Does that make sense? Does that help? Griffin.
So there are the three types of dampening processes. What happens if, are we going to have to know what happens if there is no dampening present?
Everything that we've done in this class has
So we don't have to
damping.
So there won't be any.
In your controls class, you will need to know what happens.
Okay, so then we'll discuss.
When you get to 30-50, you'll need to know what happens there. Basically, what happens is your system breaks.
Yeah.
Well, effectively, here's the whole thing. With damping, what you want is something to eventually stabilize at a level you're designing for. When things become undamped, the exponential goes the wrong way. And you have a positive value in your exponent. And so instead of, let's say it's underdamped, instead of it oscillating and then eventually damping out and seeming like it's no longer sinusoidal, decaying, now what happens? Imagine you have your sinusoid and now it's ramping up and now it's just shaking violently. And then your machine comes off the floor and breaks bolts and crashes. Not so good for real world mechanical systems. So undamped systems generally are not preferred. What else? Everybody's all good on chapter 8? We've pounded to death second order Diffie Qs.
We don't have to first and second order stuff. I was just going to say, we know how to do the Laplace transform, but no.
Should know how to do Laplace. Should know how to figure out which of the three damping types it is. Should know how to solve for those coefficients. Should know your alphas and your omegas. Comprehensive finally. That's right. Yep.
Anything that has been taught is very important.
Here we go with Riley's 8 minus 4.
That's what I was
That's the thing,
Well,
right?
top
Anything
five
that's been taught.
classic has it.
It was taught.
Yeah.
It's on video. Thank you.
So for the energy and like a capacitor and the
Mhm.
energy in an inductor, we just really
Wait, are we
need
getting
to know the
recorded?
equations to that.
Yeah, just put that on your sheet.
I'm gonna wait for myself.
Well, he's got the same way.
It's like, it's just looks so.
Anything else?
Score is 8.
Satisfied?
Alright, so you said 4 pages would be sufficient as long as just the front.
4 pages one-sided or 2 pages double-sided, either way.
11 o'clock.
11 o'clock, I believe. Yep, right here.